Hi everyone, welcome back to the weekly ZX seminar. Today we have Julio and Josias. They are going to tell us how do they use ZX calculus to study quantum error correction. And the floor is yours.
Yeah, thanks a lot for the invitation. We are. I'm gonna start. I'm Julio, PhD student from Berlin, and Josias will do the second half of this presentation on this paper that we put out on July on the archive together with Alex, who you might know from the ZX community, and Manuel and Marcus and Jens, of course, as well, about an error correcting protocol, which we call the XYZ Ruby code, and maybe more importantly, the methods we use to study this protocol and how this is related to the ZX calculus or to. So let me start by giving a short overview on what active quantum error correction is all about. So imagine you want to run some circuit, simulation, you want to run some algorithm, whatever you want to do. And now you run the circuit, and at the output should be like close to what you expect the state to be if you perform this operator on the input state that you want to implement. And you might ask yourself, is this possible even if there's noise or like errors happening throughout the computation, or if there's even some imperfection in the preparation or the readout? Turns out, unfortunately, that the physical fidelity you needed to have to do this reliably is way too small. So this is not possible to do physically. Like no hope in like any reasonable timeline that technology will have these fidelities. So one way to circumvent that, one promising way, is to use active quantum error correction, where we use an encoding of our physical state, of our logical state, that's like 2 to the k dimensional and k qubits, into a much bigger space of n physical qubits, which you could imagine being depicted by some encoding map into like this bigger space. You apply like an encoded version of the circuit you want to run, and then in the readout you do kind of the inverse by solving a decoding problem. And turns out that very early people have realized that this is in principle possible if there's like minor assumption of like what type of noise happens. There's a famous threshold theorem telling us that this can be achieved. Often you might want to think about, similar to how the circuit on the top is like a sequence of elementary operations, you might think to have some elementary encoded operations as well. And it's an active scheme because we kind of apply measurements that have an active feedback on the system and gives us information about possible errors that occurred. This has to be contrasted with passive error correction, like in a magnetic hard drive for classical information, which just you don't have to do anything actively. But this is much more tricky for quantum systems. And so when you analyze such a protocol, it's indispensable to keep track of how operators evolve through the system. For one, to understand how the encoded information is manipulated, but also how errors act. And the goal of this talk is kind of to show how graphical tools can be used as a versatile and efficient method to track these in the Clifford case. Okay, so this talk is composed of 2 parts, where the first part is presented by me and giving introduction into the method and introducing something called the Pauli flow, or some people might know it as Pauli webs, and could think of it as a graphical stabilizer formalism. I will give meaning to these words shortly. Then the second part will be done by Josias, where go more into the error correction side of things and show how the quantities introduced in the first part play a role, or will be used in error correcting analysis. To lay a bit of groundwork, let me start with the stabilizer formalism, which is essential if you want to work in error correction or study these states. And stabilizer formalism is based on the Pauli group, which you might all know. I just, for completeness, put it on this slide. You can think of it being like on a single qubit, the Pauli group being kind of generated by these 2x2 matrices. Similarly on n qubits, you just have all possible tensor products thereof. And there is an efficient way to describe like many body state or many qubit states in terms of eigenstates of these operators. So if you think of the computational zero state, you can say, well, all the coefficients in front of my state as like a vector in a complex vector space are zero except a single one, which is has a 1. Or you can say, well, it's a state that is stabilized by the group generated by the single Pauli Z operator. These is two equivalent descriptions. And similarly, for many qubit systems, this generalizes, of course. And in order for this description to be non-trivial, the group has to be abelian, and -1 shouldn't be in there. And for, especially if you scale up, think about like many, many qubits, this gives a much more efficient way to describe states than just keeping track of the coefficients in front of the vector in this exponentially large space. The Clifford group is also an important part, is namely the groups that maps Pauli operators to Pauli operators. So if we have when you have physical operations, gates that are composed of these Clifford operations, then we can simply keep track of the stabilizer groups instead of keeping track of the states. So in this way, this gives us an efficient way to like understand Clifford protocols, and this has been used for many decades. And we want to do this graphically. So to do this, let me introduce a notion of a stabilizer tensor. So a n-legged tensor is defined by a collection of complex numbers indexed by the basis elements of an individual component of this space. So say you have n qubits. This is a 2 to the 2n dimensional vector space, and you can think of all the coefficients as like a complex number and can group these complex numbers in these t's. So if you can think of, and you can think of this graphically as if you have this collection of complex numbers, they define a state in this big space. And we define a tensor that, if you interpret it as a state, like shown here, is a stabilizer state. So it's uniquely fixed by a abelian group of Paulis, as shown on the previous slide. We call this a stabilizer tensor. And graphically, we can depict a stabilizer of this tensor by the following equality. So we can freely kind of fire and absorb these n-qubit Pauli operators around, acting on each individual component of the tensor. Now, having two tensors, they are particularly useful when you think about tensor networks, so contracting these blocks along a subset of edges. So here I denote the subset by C. And what this simply means by definition is that I identify the values of the I identify the values of the bases associated to the legs that are contracted. So here in C, so all these CIs are the same for T and T prime. And then I take the product of these and sum over all possible basis configurations. And this can be understood as a new tensor because this evaluating the sum just gives a new complex number, new tensor. And it turns out that what we proved is that if T and T prime are stabilizer tensors, T tilde is again a stabilizer tensor. And the way that the proof works is that you kind of want to construct the stabilizer group from the stabilizer groups of these individual components. And we did it with like you construct a group and then you show it's actually full rank. So it actually uniquely determines this T tilde tensor. There's no additional degree of freedom left after this assignment. And the algebraic methods are very group theoretical and highly inspired by the paper that I show here.
I have a question.
Yeah, for sure. Go ahead.
So I understand that every tensor stabilizer tensor corresponds to a maximal stabilizer group. Is that correct?
Yes, yeah.
So let's say you have S1 and S2 be two maximal stabilizer group, then there's no guarantee that every element from S1 would be commute with every element from S2, right?
No. And this is exactly what you kind of need to solve in this proof, is how do I still extract this full rank stabilizer group when contracting? And graphically, this would correspond to like which kind of Paulis can I push through both tensors and then annihilate in the middle along the contracted edges. So it's only it's about the stabilizers that kind of overlap on this on the edges that are contracted. If there are stabilizers that overlap, they can they are kind of preserved by this contraction. And what we show is that whenever they don't overlap, which means that there's somehow some non-commutativity going on, they are not preserved through this contraction in a way.
And in that case, are you essentially doing gauge fixing in order to find the combined stabilizer tensor?
Yeah, so the paper I showed here with the star is exactly on how to algebraically understand like code switching and gauge fixing. So and the methods are very similar, yes. So you can, but it's important to note that this statement holds for arbitrary bipartition of leg. So you have input and outputs, but you can like do this arbitrarily. I didn't do any conditions on C. So yes, it's like it's using the same algebraic methods that tell you how to understand two different gauge fixes, but yeah, it's kind of an application thereof in a way.
Okay, thank you.
Cool. So this fact that you can compose stabilizer tensors to get new stabilizer tensors raises the questions, are there nice elementary building blocks with which we can represent any stabilizer tensor network? And turns out you can. You can, for example, use the Clifford ZX, like the Clifford fragment of the ZX is one example of such a choice of elementary building blocks. And sorry that I use maybe to those who might be familiar to a different color choice. But that's the colors we used here because we think that XYZ and red, green, blue fits very well as like an assignment. So the Z tensor in the ZX calculus is we denoted with blue, and in terms of these sets of complex numbers that I showed 2 slides ago, they are defined by one tensor that takes this delta form. So it's 0 whenever at least two so A, B, C up to D takes the values in 0 or 1, and it's 0 whenever they are different, and it's non-zero when they are the same. So it's kind of diagonal as a matrix. And then we keep track of, we have this classical label S, you can think of it as a pi phase in the X calculus, that attaches a sign of -1 if this value is 1 or not. Similarly, there is kind of a dual tensor to that, which is 0 whenever the parity is even or odd on the associated basis configuration. So this is a definition, and it turns out to be useful because if we work with Pauli matrices, they have a very natural representation in terms of these tensors. Then we can represent Pauli Z and Pauli X matrices, hence also the name the X, I guess, by like these signed versions of these tensors. And they are dual to each other in that you can apply unitary, a Hadamard, depicted by like a box, to every edge that goes out of that spider to map from one to the other. Moreover, they obey the relations that you can like split and fuse them, and thereby like adding the sign mod 2 or mod 2 pi in the if you want to think about the x phases. And some other rules that I don't want to go into more detail, like what the complete set of rules are, but I want to highlight one relation, namely the one that for the red tensor, you can apply a collection of Z matrices, so signed tensors of another color to every leg, and these can be absorbed into the tensor. So you, again, already might see a similarity with the stabilizers I showed earlier. And depending on S, you might acquire a phase or not. So for example, the blue spider has these emerging symmetries that for each pair of legs, I can kind of use the first relation on the left to first move one into the tensor, then the other one, and then mod 2 makes it 0. So the first equality is clear, and the last equality is kind of just a dual of the one I show on the right-hand side. And if you do the counting, you find that there's n independent of these define n independent Pauli operators. In this case, pair of z's for each pair of edges ij, and like this x1, x2 times x3, and so on up to xn times the phase depending on this S. And they define a stabilizer group of that tensor. Same for X tensor, just Hadamarded. So after this recontextualization of parts of the Clifford fragment of the X, I want to motivate how we came up with a third color, and we just thought, okay, let's just take the same approach and use a basis transformation that maps Z to Y instead of Z to X to define a new color, like the Y color, or like Y tensor. And if we do the calculation, this is the coefficients that you get out if you use this unitary. And so now you find that in contrast to the other ones, you also have complex entries, like there's an I. And this is a bit tricky to work with because now transposition is not daggering anymore. However, this can be easily fixed by introducing this additional notation that we say, okay, we kind of complex conjugate the vector space of each individual leg by adding this extra orientation locally to the tensor. And this just means that we assign this -1 in the exponent instead of a +1 to this tensor. If we do this, we end up with the Pauli Y matrix as being depicted by this tensor, which now is less symmetrical than the ones before. Like we have now this one direction going in. But this also makes sense because if you think of the Pauli Y matrix, which is like I times the product of X and Z, its transpose is -Y. Whereas for X and Z, its transpose is the same. So there's no way we can have a fully symmetric graphical calculus if we only want to take care, if we only wanted to depend on the way that we contract the things and like orientations of the edges shouldn't matter. We have to have an asymmetry in the tensor respect representing the Pauli Y. Okay, so with this, they obey this slightly modified fusion relation in that we can now fuse two spiders if one of them, I mean, it's not a spider in the strict sense, but let me still use the word. So we can fuse the spider if the orientation on one goes kind of into the other one. So this is important. If not, we end up with additional Z matrices on the outside. Okay, so as a summary, I want to show the additional kind of rules we have for the green spider. There are a few more for this unitary that we showed on the paper. They're not too important for the rest of the talk, hence I skipped them here. But what you should remember is that with this new Y spider, we can like flip legs. And it turns out that it's the same as like kind of spawning out like a Z bubble, like a Pauli Z matrix, out of this leg. So the first identity holds. And if we flip all the legs, it's the same as complex conjugating the tensor itself. There's this fusion relation that I just mentioned. And now, very similar to the tensors, the Z and the X tensors, you also have an additional stabilizer of a different color, namely a Z, like a collection of Pauli Z matrices can be applied to all the edges of the tensor, and then the tensor will only transform up to a phase, where the phase is given by this S label that lives in 0 or 1. So again, it defines like stabilizer tensor, but just in a different basis. So we have 3 sets of tensors that are symmetric in the sense that they are all kind of GHZ states, if we interpret them as states, but just in the Z basis, X basis, or Y basis. Okay. To come back to the earlier point in that nice representations, so you might ask yourself, well, we had the X, it was nice, why do we need this more? So the point is that if you want to include Y measurements and Y operations, which are for many protocols in error correction, you want to allow for that, or even more generally, you want to kind of allow for the flexibility to maybe trade one for the other, or so transform a collection of X and Z measurements for Y measurements. Yeah, we would say that the choice of tensors we choose as a elementary or like a set of like generating set is nice because the Y measurements or multi-qubit Y measurements now have a nice representation in the sense that they look very similar than to the usual XX and ZZ measurements, which are just 2 tensors of the color that is associated to the basis that we measure on the world line of the physical qubit that we measure, connected by a vertical line that carries a tensor of a different color with the measurement label. Yes, so this should summarize this. So especially the last row is important for what we will see later.
I have a question about the YY measurement.
Yes.
So can we think of the YY measurement as you first perform a change of basis on the ZZ measurement, meaning that you're putting this shape to surround the blue circles and then you transform it to the green circles?
Exactly. That's exactly how you can understand the identity that is depicted in the last line, yes.
And
So
why here you have n and n plus 1?
that's an artifact of the definition. So if you so you need to conjugate the Z, right, with the unitary that transforms from Z to Y. On one side you apply U, on the other side U dagger. That's why there is one arrow pointing right. Now the question is, why is there a +1? Well, that is because if you add them together, the way that the red tensor in the middle, so if you were to start with the top right diagram, let me see if I can put my mouse somewhere. Somehow you don't. Do you see my mouse? No.
No.
I had this already. Give me a second. Unfortunately, it disappears once I go to the slide that I'm showing now. So yeah, so the ZZ measurement on the top right of the box, if you were to conjugate with this UU star or UU dagger, of course, and you use the equality that is on the very top of the slide to move this diamond-shaped U into the vertical line. You will find yourself with a red tensor in the middle with 2 unitaries joined. And it just turns out that this red tensor conjugated by these diamond-shaped unitaries does not map like this pi spider to like the pi spider of a different color, but to attaches like yes, like plus pi again, like it transforms it to a slightly different one. So that's why you get a +1. Mm. Yeah, you can also think about the stabilizers of the full diagram. So a YY measurement should be able to absorb a YY.
Yeah.
And this is represented by two of these green tensors that go into, like they're on the world lines and they go into this thing. And now we can use the relations that is now hidden. So the relations to fuse the green, to move the YY onto the vertical one. And you will find that to have a stabilizer of YY and not of Y times Y transpose, you need this +1 there because it's anti-commutes with the Z in the middle.
Thank you.
But it's also not so important because all these Paulis, you can, like these +1s, you can keep track offline, kind of. You only have to, yeah, up to a sign, it's usually the same. Okay. Hope this was clear. Now, yeah. I already showed you these symmetries or stabilizers of these tensors, and they can be used to absorb Pauli operators on the edges, or alternatively to propagate Paulis through the tensors, and maybe you get a sign. And now we have this more or less symmetric set of symmetries with this small change that there's this small orientation on the green tensors, but they look very similar. And we will use this in a second to propagate Paulis through the protocol and understand their effective action on some encoded information. So for this, it's important to keep track of these phases. And also important to keep track, okay, when I push a Pauli operator through, do I get a -1 or don't I? Hence, we give it a name. So we say that a tensor, if it transforms like this, under a multiplication of a Pauli, or like absorbing a Pauli, if this absorption is possible up to a phase, and then this phase has to be ± 1, because if I do it twice, it has to be the identity. We say this tensor has to be charged, has a charge S with respect to P. The language is inspired by like gauge theory and like how charges of its like symmetric models have like charges that are described by representations of this group. It's not too important. Point is, it's important for the discussion later, so we give it a name.
And is the shaded spider what you meant by the Y spider, or in other words, the green spider?
We say any tensor that transforms like this, we call this. And now it turns out that these three tensors that we have on the top, for the blue tensor, it is charged with respect to the XXXXX. The red one is charged with respect to the ZZZZZ, and similarly the green spider or the Y spider is charged with respect to the Pauli operator ZZZZZ. So they all carry charges with respect to different Pauli operators. But so for example, the Hadamard gate, it maps Y to -Y. So I would say the Hadamard is also charged with respect to YY. Okay, so now we finish the introduction with making a graphical representation of these symmetries, and that we just keep track of not the individual spiders, but we want to propagate Paulis through our network. And we do this by highlighting full edges, because in the end, we want to only consider operations where I can move a Pauli operator fully through the edge. So for this color, we, for example, represent it like this, for the other colors like this. And importantly, we highlight the charge as a graphical way to keep track of these signs. We don't want to always keep -1 to the power, blah, 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 blah. This is like very tedious, especially for very large diagrams. So we only keep track of this locally by adding this highlight, and we define a Pauli flow, or others call it Pauli web, others stabilizer flow. Choose your name, but yeah, we define it as a highlight of edges and signs that is consistent for all tensors in the network. So imagine I have like not only a single spider like this, but like a collection of these blobs connected by edges, then this Pauli flow is a highlight where I can restrict myself to each individual tensor of the network and then just look at its immediate surroundings, and then it falls into one of these highlights that I showed here on this slide, or the identity highlight where nothing is highlighted, of course. Okay, now this helps us to describe the action of a circuit. For example, for the teleportation circuit, which is depicted on the left, we can like represent it slightly easier by fusing some spiders together. I didn't do it entirely because it still should resemble the circuit to some extent for the purpose here. And it has the Pauli flows, and you can check that this is a generating set of all the possible Pauli flows that look like this. In particular, this tells us that x1, indicated by the first Pauli flow in the top right, gets mapped to x3 times a phase that depends on mx. Similarly, z is mapped from z1 to z3 with a phase depending on the measurement outcome. We can think of this as more abstractly as both sets of operators being the generators of the same, like of an isomorphic group. Like they both generate the Pauli group of a single qubit. And hence we can think of this circuit to have a single logical Pauli group, and it teleports this logical Pauli group. It happens to be fully supported on physical qubit 1 before, and it happens to be supported on physical qubit 3 after. But it's an isomorphism between groups, and hence it will always apply a Clifford action, right? It maps Pauli operators to Pauli operators for any such flow that goes through the network. Now, hopefully it's clear that this generalizes straightforwardly to a very big network. Think of a circuit, and if you know it's a valid highlight, so Pauli flow, and you have the input and the outputs highlighted, you know which Pauli operator gets mapped to which, and then if you also know the signs that are highlighted in the interior of the network, you can keep track of which signs you attach to these Pauli operators. So generically, you will expect 3 different types of flows. Ones that are purely internal. And this is just a classification for now, just independent of anything more. Like it's just, tell you, you can highlight stuff, and then I say, well, okay, it naturally falls into 3 classes. Namely, things that is only highlighted in the interior, stuff that only highlights edges on either side. Like there's no non-trivial connection through the bulk of the circuit. And then there is what we call logical flows that you have seen an example of just now, where the input and the output are both highlighted in a way that you can't decouple them by applying other flows. And this fully captures the kind of effective action of the circuit, and also helps us to understand the error correction properties of the circuit, which Josias is gonna talk about now. If there are no questions, clarifying questions on the...
I have a clarifying question. So if you go back to the previous slides, actually 2 slides ago, yeah, like this one.
Sorry. Yeah.
Right. So how we color the edges is not unique, right? For example, if you look at the blue edges, or so suppose you're propagating a Z gate through the this Clifford teleportation circuit, then you could either propagate Z to the second wire or propagate it to the third wire by the fusion rule. Then in that case, does this matter?
Locally, you're right, but there is a unique group of Pauli flows of the whole diagram, right? So you can, if you can propagate a Z through a blue spider in either direction, but as a Pauli flow, we only count the ones where you can propagate it fully. Either internally, they cancel again, or they go from input to output. And the set of these propagations, right? It's not a single one. It's not local. It's not an individual stabilizer of a tensor, but it's really a certain combination of stabilizers that cancel out in the interior. Yeah, and this is why it's like a non-local property kind of. Because if not, it would just be the X rewrite, but it's kind of dependent on the context, you could say. If you have a subdiagram, you don't know, without knowing the context, you don't know which Pauli flows are supported on the subdiagram. You need to actually know like the full diagram.
So knowing the full diagram will tell you whether you choose the flow that connect input to the output, or it's a flow that is connecting input to input, like the one that is internal.
Exactly. And in general, they form a group, right? So you can have these two flows and I can add them together. And then according to this rule that I show on the top left, that green is equal to the sum of blue and red, up to some trickiness with the signs you have to take care about. But this is all formalized in a group structure to a quasi-Pauli group. So where you ignore the phases and then the signs tell you what phase you get.
Thank you.
Okay. There are no other questions. I think I would stop sharing and give Josias the stage.
Yes, can you see my screen?
Yes.
Top. Okay. Yeah, I will take over the second part of how we can now use this graphical calculus that Julio introduced to analyze quantum error correcting codes. Again, if there's any questions, please interrupt. In view of time, I'll go not too slow, but yeah, whenever there's something unclear or I use too much jargon from the quantum error correction community, yeah, please interrupt. In the second part, I will start again with these generic flows and show how we can think of these types in the context of quantum error correction, then introduce what we call a probing protocol, and then show as an example for the XYZ Ruby code how we used all of these ingredients, put it together, got out a detector error model, which we can then use to actually get some numbers and some results. Okay, first I want to go back to a relatively basic introductory example of the repetition code. So the repetition code, it's a stabilizer code, which could be part of this first encoding step that Julio showed in the beginning, where we have n physical qubits, and our logical states, 0 and 1, are specified by the +1 eigenspace of n-1 stabilizer generators, such that we encode one logical qubit, which just measure the adjacent Z parity of these qubits. And then we have logical operators, a logical X operator that flips 0 to 1, that's supported on all of the qubits, and a logical Z operator that can just choose to be on qubit 1. That then flips the phase of the one logical operator. In any error correcting protocol with these codes, a crucial step is to measure these stabilizers, because they define in the +1 eigenstate the state of the logical state with their +1 as being a +1 eigenstate. So we would measure these stabilizers, and in particular, we would measure them repeatedly. So such a circuit for measuring a ZZ operator would look like this in a classical quantum error correction or quantum computation circuit in the RGB tensor network or in the ZX calculus using the rules that Julio showed you. We would have this part of the circuit depicted as this small block on the right. We can then look at all these three different flows that Julio has introduced. First, completely internal flows. We can, for example, find this internal loop here. You can see at every blue spider, the requirements are fulfilled. That two blue highlights go in and out, and we also have these tensors charged with respect to that flow, these measurement tensors. we will find in and output stabilizer flows as such. And we will also find logical flows that highlight both inputs and outputs. This time in two colors, we have a blue Z logical flow that can just go through on a single physical qubit. And we have X logical flows that at every blue tensor have to spread all over, so it actually lives on the full repetition code. Now here I'd like to mention two things. First, if we would, for example, take this detector flow on the left and just cut off the first part of the tensor network, then we would, then this would result in turning this detector flow into an input or output stabilizer flow, which would not happen on the logical side. If we cut here, the logical flow stays a logical flow. A second observation is that, if we look at the Paulis supported on the physical qubits, for example, on this in this detector flow, then this Z1, Z2 corresponds to a stabilizer of the protocol at that time step. Same in the logicals. Here we would have a product of all x's, and here we would have just a single physical set. Okay, these, as you can now already probably guess that we will use these detectors and in and output stabilizer flows also from their name for quantum error correction. And for that, I'd like to go back to the symmetries. In particular, if we take this detector Pauli flow, we can go back to forgetting about flows and just putting the symmetries, for example, the symmetry of the red tensor here, and also the symmetry of the blue tensors at every single tensor here. And we will get a completely like the same tensor network. Now on the right, we can then use the fusion rule, for example, or just realize that Z squared is identity to find that this left tensor network is actually the same as the one on the right with a constraint on our measurement outcomes. And this constraint that the sum of the measurement outcomes has to be 0 in order for the left and the right tensor network to actually be the same, then allows us to do error correction. How is that? Let's say we place some fault, say a single qubit X fault here on in our network after the first ZZ measurement. Then this constraint from before changes. In particular, instead of evaluating to 0, the sum of these measurements would evaluate to 1. And we can therefore detect this X fault. Just if we run the same protocol, we know without faults, these measurements should evaluate to 0. Now we introduce this fault and we know these measurements, and if we know these measurements now evaluate to 1, this is a signature that a fault has happened. We can also check the action of these faults on the logical operators. Now this fault is not judged with respect to the X logical flow and therefore also does nothing, but for the Z logical flow, it actually flips the value of the logical operator. And therefore it's a detectable fault that also has a consequence on the logical information. However, if we can correct for it, then it's not a bad consequence. Okay. Next, I will zoom out a little bit and ask how do we now benchmark these protocols. So say we have some code and we want to see how well does it protect our information. What we typically would do is we run D rounds of stabilizer measurements to check whether for example, if we started in an all 0 state we perform d rounds of error correction. After the first round, we've initialized a zero-logical operator, a zero-logical state. Then we perform rounds of error correction and then measure out, for example, a single qubit Z to check how well was this protected by our rounds of error correction. This is then called a Z memory experiment. And the same thing we can do in the RGB tensor networks, but now it's a little, we actually get a little more in some sense, namely the following. Here we have now a very generic RGB tensor network where this repeated ZZ measurement might be part of, but in particular, independent of whether it's now X, Y, or Z, we have some detector flows, we have some stabilizer flows, and we have just some logical flows. They don't need to be an X logical operator all the time. They can also change their color through time. Now, to benchmark this bulk protocol, similar to the circuit where we initialize and read out, we can add an initialization and a readout layer and use this concatenation that Julio has shown you to get a new network that is now there's now a tensor network without any open legs. Now this tensor network without any open legs is kind of like a matrix element probing of this huge tensor, and therefore we also call this a probing experiment. And there's a few things to note. First, as I think Sarah, you already hinted at, some of the stabilizers, they might not fit to or some of the stabilizer flows might not fit to what we attached through there. So for example, this red flow here, there's no way because the red tensors that we attach there only have blue highlights that this one survives. However, for blue output stabilizers, we can close them up with the corresponding blue flows of our input layer. Now, in this generic picture, we now initialize in a zero state and measure in X, which maybe sounds weird from a quantum error correction benchmarking perspective, but because our logical operator underwent this transformation to red on its way through time, if time is going upwards, then this totally makes sense. And with this experiment, we will kind of measure how well this operator survives through time. Now, because we have closed it, actually each of these flows is now a detector flow, because by definition we have said that internal flows are detector flows, and now there's no outgoing leg, so there's no way to it's now a detector flow. And by that it also has a defined value, so the sum of our measurements should be charged with respect to these flows should be 1. This maybe doesn't make sense from well, how do we now probe it? How do you get some numbers perspective? However, because these flows, they come from logical and stabilizer flows, there's a natural distinction in different flows, which we then use for the actual benchmarking. So if we say we put some noise model in our circuit, and then we declare typically local detectors now to decoding flows. So with these local detectors, we try to detect these faults and correct them, and the global detectors, which come from logical flows, we declare them as observable flows in the sense that after we have used all the information from the local flows to get rid of as many faults as possible, to go back to the code space, we check, did we keep the information in these global flows, did we keep it alive? So this will be our observables. Okay. Now there's tons of other experiments you could think of. For example, instead of choosing global flows in time direction, you could also choose in space direction. But we will now stick with this because it's kind of a standard experiment to check how well can we keep a logical zero state alive. Okay. These are basically the two inputs that we need to finalize our benchmarking. In particular, we will we will build this RGB tensor network with all its detector and observer flows. We will have some noise model, so some one spiders that we can place at some locations with some probabilities. Most of the time inspired by the actual quantum circuit that will be performed on a device. And from these, we will build a detector error model, which we will use for decoding. This detector error model, and now this will be a little more high level. I will not be able to go into detail. But this detector error model basically just asks what detectors and what logicals are flipped by such an elementary fault of our noise model. We then put this in matrices. So if, for example, this elementary fault Fj flips some detector Di and some observable like this one here, OK, then there will be ones in the corresponding matrices and 0 if not. These matrices then, the detector matrix, in particular, the detector matrix then specifies a classical linear code, which where you can then, in principle, use all of the tools that classical decoding gives you to perform to get an error guess. In particular, what we would do, we would, for example, sample fault configurations and then calculate using this detector matrix a syndrome and also a logical outcome. This syndrome is what we have access to when we in our quantum error correcting protocol because it comes out of all the measurements that we do. Now, in order to now decoding then corresponds to finding some sets of faults which we don't know which have the same syndrome. So these syndromes will be input to some decoder. We can use the priors to get some information, to use some more information, to get some logical prediction. And this logical prediction, if it's the same as the one that we actually observe, we will have a success. And if not, there's going to be a failure. All right. This is the general introduction. Now, if there's no questions, I will spend how much time do I have left? Another 5 minutes?
Well, because we start late, so you have another 5 to 10 minutes.
All right, perfect. That's all I need to show how we use all of this and how we used all of this to analyze a new Floquet code, which is a inherently dynamical error correcting code. Floquet codes were initially introduced by Hastings and Ha, or like, the term was mainly coined by Hastings and Ha in 2021. Floquet codes basically use repeated measurements to do error correction. And the main difference from standard error correction protocols is typically from one round to the next, the measurements don't commute like the stabilizers commute, and also they're pretty low weight, which has practical implications. Now the Floquet code that we analyzed, we called the XYZ Ruby code, because the space it lives on is this is where we put these physical qubits here depicted as black dots on this hexagonal lattice, which has doubled edges or tripled vertices, however you might like, which is also sometimes called the Ruby lattice. And then every colored edge, R, G, and B, corresponds to a two-body XX, Y, Y, or ZZ measurement, which we will do in a specific time order. So for example, we could just measure first all the XX edges, then the YY edges, and then the ZZ edges, and then repeat this forever. Yeah, typically what one would do or would have done in the past is we look at what we measure and we track our stabilizer group throughout our sequence. So for example, I want to just do a very short example. If we measure XX operators, we will project into some eigenspace of these. In the next step, if we measure Y operators, then these Y operators anti-commute with the X edges. However, the product of all X edges is still commuting with the Y measurements and will therefore still be in the overall stabilizer group. And let's say in the third move, in the third step, we measure the ZZ operators. Then these Y edges anti-commute and the X operator anti-commutes as well. However, the product of Y and X, which is the Z operator, commutes with the Z measurements and will survive the stabilizer group. This you will have to do for all the possible operators to find generating groups and then check whether blah blah. It's like doable, but you can also do a lot of small little mistakes. So I just flash you the result of this analysis before going into the little bit more beautiful analysis that we can do based on the three-colored graphical calculus that we developed. Okay, so let's switch gears back to three-colored graphical calculus and RGB tensor networks. So here on the right, you see just time going upwards, one of these big plaquettes. So every vertical line you can think of as a data qubit world line, and then the Z, Y, and X measurements are shown by blue, green, and red horizontal lines respectively. The first step, as I have done with the repetition code, is find the detector and logical flows. So for the XYZ Ruby code, if we want to find the detectors, we will place the highlights and see if we can find highlights that are local and closed and inside our bulk. And we find, for example, these two flows. And what you can see is if we look at this detector flow and the measurements that are charged with respect to these flows, it will correspond to 3 YY measurements, then 3 XX measurements, which is the same 6-body Z plaquette that I've shown you before. And then if we continue, we will see that it's again this X measurement and then a Y measurement on the same edges, just a time step later. So what basically this detector does, it reads out this Z plaquette here twice, and because this Z plaquette also is it's a stabilizer of the code, and we have basically read out the stabilizer of the code twice, which we can use for error correction. Now, this is the symbols of detectors that you can find in this code. We have found another set of detectors which are related to different stabilizers, and we have also found logical flows that span that go once around the torus, where we put this Ruby lattice on, and in time go from beginning of time to the end of time, and are therefore logical flows with in and output. Okay, once we have found those, we will design a probing experiment and define an error model to then benchmark how well this protocol works. So in the next step, we take two thin layers and attach it and see what survives and what not. So for example, for this logical flow, it changes colors. So it starts as being a Z-like logical, then changes to green, and then back to blue. So if we start with logical with physical zeros, which support blue flows, we can initialize in this kind of logical very naturally by just starting 0 and then initialize and then starting by measuring Z operators, because we can attach this red spiders with their blue flows to that. The same works with logical zeros, with physical zero states for the other logical, which is maybe not super surprising, but interesting, because typically to initialize the other logical, you would start with physical plus states instead of physical zero states. But because the logicals change colors, this allows us to also start in physical zeros and initialize in the other logical sector. Okay, after that, we then can also use these tensor networks, and that was another question or another comment from before, that the Y measurement is basically a Z measurement where you do basis changes on your data qubits, and this is in fact what we can do. We can use rewrite rules to kind of compile down our the RGB tensor network to operations that we can support in the quantum circuit. So for example, here, when we start with the Y measurements and the X measurements, we do some basis changes to in the end have a circuit compiled that of only Z basis initialization and measurements, C knots, and single qubit rotations. We then also, and there are no details, we then also get this detector error model on which we can do decoding. We use full circuit level noise. So everything, initialization, measurement, single qubit, two qubit gates, and idling positions have some error probability P. And what we find is that if we do this protocol and we increase the size of the code, so we go from order 10 to order 100 qubits, we will suppress logical errors more and more, and we also find a threshold up here in the region of about 0.2%, which means that from a physical error rate that is below that, increasing the code will suppress logical errors more. Okay, with that, that's all that we wanted to show you. Julio will do the first half of the open questions.
Yeah, there's a few open questions on the general side, if you're interested. Can answer questions on that. So namely, there's a question of can we actually find can we extend this beyond Clifford circuits, maybe the most natural question, and do graphical representations help us in understanding a getting a more unified perspective on what it means to be error correcting or whatnot. People have understood this for certain examples of classes of codes or so, but there's a lot of research going on in code design, so finding good subspaces into which we can encode information in a very efficient manner, and finding this version for the full circuit would be an interesting open question to tackle. And
and then for the concrete code, we have also more open work. We now use a very general purpose decoder, but we think that the specific code might allow for a more adapted decoder that maybe even allows for better performance. And then also right now we live on a torus, and we want to put it into a planar land, and we already have shown in the paper a few comments on how this can be done, but still needs to be worked out properly. Okay, and with that, we'd like to thank our collaborators and you for listening. And if there's any more questions, go ahead.
Thank you both for the very interesting talk. So you can use emoji to claps or raise hands.
I never really studied the quantum error correction stuff, but how does your work relate to like the bigger picture to give me more of an intuition how to put this?
Yeah, so in the bigger picture, we are on the, let's say, maybe on the verge of making fault-tolerant quantum error correction a reality. I don't know, we have the first experiments that show, yeah, we might go beyond break-even, maybe we are beyond break-even, so logical operations outperform physical operations. Yeah, kind of the Floquet codes, they and our codes, they kind of place themselves as interesting candidates for exactly in the time towards fault-tolerant quantum computation, because the main limitation is still, I mean, theoretically, people would know how to perform constant overhead fault-tolerant quantum computation, but then you need to do it on an actual device, and there you often have very high architectural constraints, and Floquet codes living on a one sec, yeah, like nearest neighbor lattice, and working only with two-body measurements are kind of they don't have a lot of architectural constraints, right? If you have nearest neighbor connectivity, you can in principle implement this. You may need measurements, which are in some architectures not as good, but yeah, that's why, or one reason why Floquet codes are interesting. Another reason is logical gates. Maybe Julio wants to add a little bit to that, or also to like the graphical calculus part of the talk.
Exactly. So there is also the context of so a big open question I would say is general how to perform like protected logical operations. And so far we have only discussed these probing experiments that Josias laid out, is that you preserve a single logical and you probe how well did I perform the identity gate essentially over time. And there are certain no-goes that tell you can't do. So if you have a code like this is defined by like only like a nearest neighbor or next to nearest neighbor, some finite range interactions. These codes cannot support a universal fault-tolerant gate set. So like so we have to kind of find ways to and design and understand ways in which we overcome this by doing something like code switching or finding other ways to do gates. And I would say that these graphical representations added with what we call Pauli flow make it much easier to understand these protocols, where you can kind of abstract away the microscopics to some extent to guarantee that logical operators are mapped to each other in a certain way, which then tell you which logical gate was applied. Yeah, and in this dynamical setting, as you see, outlined, like you would need to like look at it like instantaneously, like cut by cut by cut, and track this everything algebraically, and this can be quite tedious. Whereas the graphical representation helps a lot in understanding this, coming up with new protocols, yeah, and so on.
Okay, thank you.
So I have a question. When Josias first talked about this coloring of the or like introducing the Pauli web, you're talking about using this Pauli web to look at the Pauli propagation. Is this like my understanding correct? And in that case,
Yes, yeah.
Okay, in that case, if you start with an error correcting code with distance d, how is this d related to your conclusion of the Pauli webs or how Paulis are propagated? Do one imply the other, or they are two different things?
So if you cut what Josias said, if you cut the network and understand this, say the boundary of the cut along the cut as like sets of physical qubits, then the highlights give you a Pauli operator. If you cut a logical flow, having a distance d code means that this Pauli word will have at least distance d. You can also devise a restricted error model. And in this restricted error model, where you're only allowed to place errors on the physical of the world lines on the qubits, so it's defined with respect to choosing world lines of qubits. If you pick just this restricted error model, then you will also know that the minimum weight of a bad fault that is not detectable is also bounded by the distance. But in general, the spacetime distance, so the number of faults you have to at least place such that it will flip a logical without us noticing, is differs from the one of whatever cut. But you can take a cut and then you will have some stabilizer group at that time, but it will never, like there's no guarantee that the distance of the stabilizer code is actually telling you anything about the distance of the protocol, because circuit elements and like depends on your faults, on how Paulis can propagate.
Yeah, I was just adding, you can think of it as like this going backwards, then you have some new stabilizer group, and if, I mean, of course, if you at any time step you do this and your code always has distance d, then under the error model that you defined, so you always have to place at least d faults that you to be undetectable but flip the logical, then yeah, you have distance d throughout the protocol. But yeah, this, as Julio then in the end said, this depends on a lot of things. Also, how you translate your tensor network to a circuit. So the good thing about the two-body measurements is also that they're naturally fault tolerant, in the sense that you will never, if you have some fault like appearing on this ancilla, which you just introduce to measure, it will never propagate to a fault that is uncorrectable afterwards. If you had another code than the Ruby code and do the same thing and translate it naively to a circuit, you might end up with a non-fault tolerant circuit where the fault distance is reduced or to like half or even constant.
So
this is also more quantified in this recent paper by Benjamin, Alex, and forgot the middle author, but from Oxford. You look at
Bodhi.
Yeah, right.
Okay.
They quantify this a bit more, but like it's exactly the thing. We also comment on this in the paper. It's
so if we flip the coin, so suppose you would like to combine two stabilizer group and then you want to reach let's say some new stabilizer group, then there is no unique way to find this two composed element, right? This is also like kind of mentioned in this Viola paper that you mentioned earlier, is they are talking about different ways to do code switching. And they commented that there's no unique way to find a subsystem code as an intermediary one. And determining what the intermediary subsystem code to choose is related to the gauge distance, meaning that you look at what happens when your distance change going from one stabilizer group to the other stabilizer group. I wonder, is your Pauli web capable of also talking about the gauge distance or the intermediary distance?
Yeah, I would say it's more general than this intermediate distance, in the way that usually if you think about the code switching from stabilizer A to stabilizer B, you can define a group that is generated by the union set of the two. This is this gauge group that you talked about, and then this is a subsystem code. People have looked at this. Now you can think about these two stabilizer groups as a gauge fixed version of this, and then you can kind of instantaneously go from one to the other by like measuring the associated operators, like fixing the gauge. This is not there's no unique way for one, but also this might not be the best way, fault distance wise.
Right.
In general, I would say if you have two codes, like you have some block where you have some stabilizer group coming out, and then another one that is a different stabilizer group coming out, the task you were describing is to design a thin layer of circuit that has the associated stabilizer groups as stabilizers on input and output. Like it's a thin transition layer, kind of. It's a transition matrix from one code to the other.
Yeah.
And you can actually use so you can do this thin layer. You can then this layer will be uniquely defined by the constraints you set. Namely, it will be defined by the input and output stabilizers, as well as how the logicals will be mapped to each other exactly. And you can start with a minimal representative of this thin layer. This is uniquely defined. It can be efficiently found. You just find a ZX diagram that has this property. And now you can start making spiders bigger, like splitting them up and so on, introducing new loops to make it like more protected. I don't know of any quantified way to do this, but I think that Pauli webs is exactly the way to track it, because they give you exactly the constraints that, like the minimal constraint that this thin layer needs to fulfill to do what you want to do. And then you can start maybe using the work from Oxford, for example, optimizing over different ways to realize this thin layer as some circuit.
Right, and then you can read off this circuit as your stabilizer, or like as things that you need to measure in order to do this switching between input and output.
For example, yeah, right.
Cool. So just now you mentioned this space-time distance as opposed to the regular code distance, which is 2D that we're used to. So I understand when you talk about the distance now, you're thinking about how long a logical information survive in your system. Is this correct?
Okay, I will first talk about what I mean with fault and space-time distance, and then because I have the more so for me the fault distance is I have my error model where I place faults, and I like to make the distinction between error and fault, where an error is like living on some state and the fault is the actual thing that happens. And in this noise model, I might say, okay, I place these and those faults with some probability P. And then for me, the fault distance is just independent of space and time. I look at this full thing and I place faults with growing weight. And whenever I have basically the smallest weight of faults that I can place such that they are not detectable, but flip the logical so that they all the decoding flows basically evaluate to 0, but some observable flow evaluates to 1. That would be the fault distance for me. And that's often related to this space distance, because when we have a fault tolerant readout circuit, then it's just a space distance all over, but it's more general than that.
Sorry, so fault distance is AKA space-time distance. And then fault distance is when your decoding flow does not report error, but observable flow report error.
Exactly, yeah.
Okay.
And then the minimum weight of a fault configuration that produces such an event would then be the fault distance, or the minimum fault distance. And then because this is all linear, it's also it works out in the end. It's the same way the regular distance does. That you can correct up to d-1/2 faults and so on.